I'm really excited and very happy to have Dr. Claire Malone with us today, who's traveled from London. Dr. Claire Malone is a physicist, and her passion to understand the physical world led her to complete a master's in physics at Imperial College. The root of her interest is in understanding the behavior of fundamental particles that comprise our universe. During her PhD at the University of Cambridge, Dr. Malone analyzed data from the LHC at CERN to search for evidence of supersymmetry and to improve the accuracy of the Atlas luminosity measurement. Throughout her career, she's had to devise techniques of studying to negotiate the fact that she cannot use a pen or keyboard directly due to her physical disability. Dr. Malone is passionate about communicating her enthusiasm for physics to as wide an audience as conceivable, as well as advocating for the inclusion of groups that are typically underrepresented in STEM. She's a regular contributing columnist for the magazine Physics World. She's delivered a TED Talk with approximately 2 million views. She is regularly invited to give keynote addresses at conferences focusing on scientific research and communication. And in her spare time, she enjoys reading and sometimes writing sci-fi novels. So we are thrilled to have Dr. Malone with us here today. And over to you.
Today, I would like to talk to you about why I think it is crucial for underrepresented groups in STEM, such as the LGBTQ+ community, to be visible. And about how as science communicators we have an important contribution to make to this. I will be drawing analogies with missing fundamental particles, as well as my own experiences as a scientist with disabilities. So, who am I? I have recently obtained my PhD as part of the Cambridge High Energy Physics Group, searching for a complete understanding of the universe in terms of fundamental particles. Using the ATLAS experiment at the Large Hadron Collider, LHC, at CERN. You may have seen it on the news, when they discovered the Higgs boson. The 10-year anniversary of this momentous discovery was celebrated a few weeks ago. I am passionate about sharing my love of physics, to make it accessible to as wide an audience as possible. And am a regular contributing columnist for a number of popular science publications, such as Physics World. At school, I was the archetypal nerdy kid, wanting to get the other lessons out the way, so I could get into the science labs. After leaving school, I went to Imperial College in London, and graduated from there with an MSci in physics in 2014, prior to starting my PhD at Cambridge. I have currently settled on being pansexual with she/her pronouns. However, my physical disability, cerebral palsy, has had a much greater impact on my career than my sexuality or gender identity. As I have difficulty using a pen or keyboard, and walking unaided. I have had my physical disability since birth. It means I have difficulty controlling my muscles, and hence I use an electric wheelchair to get around, and a specialized joystick to operate computers. As I have always had my disability, there was not a particular point in my education where I had to adjust to a new way of working. From the time I started school, I was learning how to negotiate my education with a disability. This can be a very different experience to someone who acquires a disability later in life. Hence, I have always had to think a little differently from other people about how to access my research and education. I dictate the majority of my work to an assistant, as although I can type with my joystick, Completing all my work in this way would be too slow to be practical. The idea of dictating equations and code may sound strange if you have never had to do it before, but if you have been doing it throughout your education, you find techniques to make it work. In the same way that I dictated my written work to an assistant, I also had to dictate my practical work. A small complication with this is that I was having to describe things that I had never physically done with my own hands. To get round this, my assistant and I met outside school hours to practice how I was going to dictate my practical exam. I was already familiar with performing lab work in this way, but my teachers and I understood that to prove to the exam board that the practical was entirely my work, there couldn't be any actions that the scribe carried out automatically. For example, if we look at the experimental setup of our friend in the left-hand cartoon on the slide, to express how to place the spring on the hook, I would say something like, take the spring that is approximately 8 centimeters long. Attach the weight that you have measured to be 247 grams to the end of the spring that has a big hook. Attach the other end of the spring to the stand. In other words, my verbal instructions had to be incredibly detailed. I also make use of on-screen keyboards that I can either type with using a joystick, or by controlling the computer with my eyes. Using technology that is also used by pilots. Sadly, I have not got on too well with voice-activated software, and perhaps anyone who has a strong accent has shared my frustrations. The focus of the next session is how communication has an important role in equity, diversity and inclusion. There has been a multitude of studies that conclude that the more visibility a minority group has in a university or research organization, the better the environment is for that community. I can see that this is true from my own experience of being LGBTQ+, since each institution I have studied at has had an active and friendly LGBTQ+ society. One such study is the report authored by the Institute of Physics, the Royal Astronomical Society and the Royal Society of Chemistry, on exploring the workplace for LGBTQ+ physical scientists. Some of you may remember it being published in 2019, or even attended the launch event for it. I think that in our roles as communicators, we have a vital part to play in elevating the visibility of underrepresented communities, and bridging the gaps between them. To give you an example of why it is so important for scientists from underrepresented groups to be visible, I would like to talk about a group of particles who are apparently not very good at letting their presence be known. Over the last century, the study of particle physics has developed a framework that describes the behavior of the fundamental particles. This framework is called the Standard Model of Particle Physics, or SM for short. The SM describes fermions, which are the particles that comprise matter, and bosons, which are fundamental force carriers that mediate the interactions of the fermions. Fermions are divided into quarks and leptons, and are arranged in 3 groups called generations. So, as shown on the slide, on the left-hand side of the diagram, the first generation would consist of the up quark, down quark, electron, neutrinos and electron. The particles in each successive generation have higher masses than those in the previous one. The bosons of the SM mediate the fundamental forces that act on the fermions. Photons for the electromagnetic, EM, force, W plus minus and Z for the weak force, and gluons for the strong force. The EM force governs the interactions between electrically charged particles, while the weak force can transform one lepton or quark into another, provided it is in the same generation. This is the force responsible for radioactive decay. The strong force is responsible for transformations between different quarks, and is the force that holds protons and neutrons together. Some of these particles, you could be very familiar with. The protons and neutrons in the nuclei of atoms are comprised of up and down quarks. The nuclei of atoms are orbited by electrons, which play an essential role in many physical phenomena such as electricity, magnetism and chemical bonds. Photons are the quanta of the electromagnetic field which is responsible for all EM radiation. However, other standard model particles may be less familiar, even though they are around us all the time, and in some cases crucial to everyday life. It would be pretty tricky, or impossible, to form protons and neutrons and hence atoms without the gluons holding the quarks together. Gluons are, of course, not to be confused with the warlike humanoid alien species from Star Trek. Life as we know it would also not exist if nucleosynthesis in the Sun did not fuse hydrogen into helium and other heavier elements. This reaction causes approximately 65 billion neutrinos to pass through every square centimeter of the Earth's surface that is orthogonal to the Sun, every second. However, as these neutrinos are so weakly interacting, we don't even notice them. The Earth's atmosphere is also constantly being bombarded with high-energy, massive particles, called cosmic rays, which originate outside of the solar system. When these extremely energetic particles interact with the atmosphere, they create showers of particles such as muons and photons, as well as pions, which are bound states of one up quark and one down quark. And then there's the Higgs boson. The particle gained its illustrious reputation by escaping detection for the longest, until its discovery was jointly announced by the ATLAS and CMS collaborations at CERN in 2012. This was possibly one of the most monumental discoveries in fundamental physics in recent decades, along with the detection of gravitational waves and neutrino oscillations. This final piece of the SM was so important to find, because it provides the mechanism through which all the other particles attain their masses. Although the more fitness-conscious particles are less than happy about the activities of the Higgs boson, it is pretty crucial for our understanding of nature. The standard model even has a certificate U version, in the form of soft toys for each of the particles, the famous particle zoo toys. We are honored to be joined today by the top quark, which Eleanor is holding up. So the SM provides us with a coherent description of the known particle content of the universe, and, with the discovery of the Higgs boson, we have observed every particle it predicts. The values of its theoretical parameters have been seen to agree with experimental measurements to a remarkable level of accuracy. So you may ask if particle physics is now just a question of improving the accuracy of our comparisons between theory and experiments. Certainly not. Unfortunately, the SM does not provide us with a complete description of the particle content of the universe, and one of the main aims of the LHC is to remedy this. Or, you could say that we need to have a more diverse group of particles to fully assemble the universe. So in which ways does the SM not provide a complete description? Well, for a start, it only actually explains the particle content of 4% of the universe, having nothing to add about the remaining 96%. We know this to be true, as the observed rotational velocities of galaxies alone suggest that their total mass is far greater than can be accounted for by just the luminous matter. This missing mass has been termed dark matter, and is predicted to account for 23% of the energy matter density of the universe. The SM can offer no suitable explanation as to the character of this dark matter. In addition to this, the unexpected discovery that the expansion of the universe is accelerating, rather than decelerating due to gravitational attraction, points to the existence of a previously undiscovered force acting against gravity on a universal scale. This force, which accounts for the remaining 72% of the energy density of the universe, and is now known as dark energy, also has no explanation within the SM. The SM also does not explain why the universe is dominated by matter particles, rather than containing equal amounts of matter and antimatter. Even in the particles we have already discovered, there is evidence of physics that is not explained by the standard model. The SM predicts that neutrinos are massless, but measurements of neutrinos from the Sun, the atmosphere, nuclear reactions, as well as particle accelerators have established that neutrinos have non-zero masses. There is also no reason within the SM itself why there should be 3 generations of particles. This is purely a fact that we have observed. Finally, there is a gap of 32 orders of magnitude between the largest and smallest scales in the SM, which seems quite unnatural. A possible solution to some of the ailments of the SM is offered by supersymmetry, or SUSY. SUSY is now one of the strongest candidates for the explanation of physics which is not accounted for by the SM. SUSY extends the SM by postulating a supersymmetric particle for every SM particle. During my PhD, I focused on searching for evidence of these particles. They possess identical quantum numbers to their SM counterparts except for a half-unit difference in spin. They also have, in the true tradition of particle physics, very silly names. In honor of the name supersymmetry, a supersymmetric particle becomes a sparticle. Continuing the pattern, a quark becomes a squark. Can anyone guess what a supersymmetric lepton is called? Yep, a slepton. I think that people are groaning at this point. Just one more. I was especially interested in finding evidence of the supersymmetric top, a stop. And I will now stop. But how can these so-called sparticles solve the problems we've found? Well, remember we said that we were missing a load of dark matter that is meant to be floating about in galaxies, keeping their rotational velocity constant with the distance from the center as is observed. We hope that the sparticles could be what this dark matter is made of. But if dark matter is made up of sparticles, it must mean they are really difficult to detect, otherwise astronomers would have spotted dark matter before now. Also, the fact that they have not been found by such sophisticated particle detectors, such as ATLAS, would suggest that they don't interact with our detectors like normal particles do. In fact, this is what we are counting on when we search for sparticles in ATLAS. We know that conservation of momentum must hold for every particle decay, otherwise something is really wrong, and we may as well go to the pub. So, if we don't detect enough energy from the products of the decay, that must mean that the sparticles have stolen it, and not been detected. I said that I was particularly interested in finding the top's partner, the stop, and on the slide you can see a diagram of a stop decaying to a top. After the protons have collided at the LHC, the particle on the right-hand side of the diagram is called a neutralino, and is a quantum mixture of the superpartners of the W, Z, and Higgs bosons. As she is the lightest particle, so decay chains stop when she is produced. She is often named as a suitable candidate for dark matter. The stop quark has a special role to play amongst the squarks. I mentioned that there are 32 orders of magnitude between the biggest and the smallest energy scales in the Standard Model. An important manifestation of this discrepancy is the lack of explanation of why the observed Higgs mass is so small. Theoretical predictions say that the probability of the Higgs having such a small mass without a great amount of tinkering with the parameters of the Standard Model is analogous to the probability of dropping a glass of water, and it landing the right way up, with none of the water spilling, that is to say, very small. To calculate the mass of the Higgs, which CERN famously measured to be 125 GeV, we have to include the contributions from all other particles. As the top quark is the heaviest quark, it has the largest contribution. But, in theory, we should find that the Higgs mass is way larger than the mass of 125 GeV that we observe. This is where SUSY comes to the rescue. When we consider all the sparticles, as well as particles, we find that their contributions to the Higgs cancel out the contributions of the particles, to leave a nice light Higgs. As the top is the heaviest particle, the top and the stop have the biggest contribution to make to this cancellation. We can think of it as a tug-of-war between SUSY and the Standard Model. The SM wants to pull the Higgs mass way higher than the mass we observe, but luckily SUSY is there to keep everything in balance. This is why, if physicists can discover the stop and other sparticles at CERN, it would be very exciting. Both from the point of view of finding a description of dark matter, and also explaining why the Higgs is allowed to be so light. And of course, we could make a load more soft toys for all the sparticles. Now, the obvious question to ask is whether anyone has ever observed a SUSY particle. Unfortunately, the answer to that question remains a resounding no. We have no evidence of sparticles, or any other non-SM particles, interacting with our detectors. Hence, in particle physics jargon, they are often called invisible particles. As a consequence, future generations of SUSY particles are not inspired to interact with our detectors either. As they have never seen any sparticles that have gone before them, let their presence be known. So the result is that particle physicists begin to doubt whether sparticles actually exist. Particularly if future runs of the LHC also yield data that fail to support the SUSY hypothesis. Hopefully you can see where this analogy is going. This is the best example I can give as to why it is crucially important that the underrepresented communities in STEM are visible. The STEM LGBTQ+ community is arguably larger than the community of scientists that have significant physical disabilities, similar to mine. As the LGBTQ+ community are now beginning to be visible and vocal about the difficulties we are facing, the situation is beginning to improve. As people have the incentive to take notice. Unfortunately, I have to say that some of the difficulties I have faced as a scientist with a physical disability have resulted from people being unwilling or unable to apply the facilities available to assist me in my studies. As some of you probably know, to get anywhere with studying physics means scribbling down equations for many, many hours a week. In my experience, universities may have supported disabled students for a couple of hours a week, but never for 50 or 60 hours. And hence recruiting assistants has always been a struggle for them. The problem is that the cohort of people applying to universities with these needs remains so small that universities are not incentivized to develop a system to support students in this situation. The analogous problems faced by the LGBTQ+ community are now only just beginning to dissipate, because of our increased visibility. And the conversations we as a scientific community are having. I hope that one day the same could be true for ambitious young scientists who just happen to use wheels rather than legs. In addition to finally discovering the currently invisible particles that would complete our understanding of the universe. A lack of understanding and willingness to support scientists with disabilities was not the only concerning trend that I noticed during my time in academia. As I am sure you would agree, the scientific principle itself relies on the sharing of information. Early scientific pioneers agreed that it was important to share ideas, show experiments to other people, and to watch and read about what other scientists were doing. In order to learn, check for mistakes, see connections and make plans. However, from my experience, I found that there is now a culture that undervalues time spent in communicating research to the public. During my postgrad, it was unusual to find a PhD supervisor that supported, or even actively encouraged, their students to engage in science communication or outreach activities. More commonly, the opportunity to participate in such events is viewed as a tick-box exercise, to demonstrate that transferable skills have been developed. The general attitude was that these excursions should be got out of the way as soon as possible, to get back to the real work of pure scientific research. I'm happy to say, I have noticed that this picture is now slowly changing, partly because the pandemic put scientists who communicate with the public on the front line of the war against the virus. The last few years have shown us that talking, explaining, listening and learning are important skills in the collective effort to beat COVID-19. There are two ways that I can see to look at science communication in relation to society, if we take a step back and view it as a whole. On the one hand, science communication can be viewed as a two-stage process. Scientists generate knowledge amongst themselves, and then they disseminate it to the public, often through the medium of journalists. An alternative view, and perhaps one that will accelerate the increasing trend for scientists to make their research more accessible, is that science communication is more like a continuum. A gradual slope, encompassing communication between scientists of slightly different expertise, right through to the communication of ideas to groups with minimal scientific backgrounds. This picture shows professional scientists, as well as all other groups involved with science communication, participating in a dialogue with groups who have a less formal scientific background. If we viewed science communication in this way, this would not only raise the profile of science communication itself, but raise awareness of the potential benefits of other activities that depend on it, such as citizen science. I would like to leave you with the thought that our roles as science communicators place us in a position of being ambassadors, or role models, of our areas of expertise, and often of science as a whole. The evidence is clear that young people are much more likely to pursue their education in STEM, and enter a STEM career, if they can see someone they identify with, who has gone there first, and inspires them. It should also be remembered that a person does not need to be similar to you, in order for you to consider them as your role model. During my time at Cambridge, I was lucky to meet Stephen Hawking, when he was guest of honor at a formal dinner in my college, Churchill. It was really great to meet someone who I read so much about and had written one of my favorite popular physics books. And I was a little shy when I got to meet him during the pre-dinner drinks. However, I have to say I was quite surprised on the day that he sadly passed away at the number of messages I got from people who seemed to think that I'd lost a great mentor and role model. I do think it is truly amazing how he adapted the way he worked to his changing physical condition. And I think he is quite possibly one of the greatest physicists that ever lived. However, Stephen Hawking is not the reason why I was interested in physics, and I wasn't trying to follow in his footsteps. Of course, I understand why people may liken my situation to Hawking's situation, but I find it quite a simplistic viewpoint. Some of my most important role models, in fact, have quite different personal circumstances to mine, and have inspired me in the way that they have turned difficult situations to their advantage by finding the best aspects of them. Most of these people probably have no idea that I consider them to be one of my role models. Which goes to show that we all have the potential to give someone confidence and support to achieve their ambitions. We have a unique opportunity and responsibility to promote the visibility of underrepresented groups, and in doing so, inspire the next generation of scientists. In taking on this mantle, we should always remember that the first step in effective science communication, as in any conversation, must begin from a thorough understanding of the needs and priorities of our audience, as well as an appreciation of the limitations of our own knowledge. Hopefully, by talking about these considerations at events such as this, both inside and outside academia. Together we can make these conversations as productive as possible. The stakes could not be higher, as we have all now seen the trouble we find ourselves in. If we try to describe the universe without involving all the willing and available people, sorry particles. Thank you for listening. I am very happy to answer questions.
Any questions?
Do you think that the situation for minorities are improving?
I think it's slowly getting better, but we do still have work to do. A few years ago at a scientific institution, there was an LGBTQ plus society, and they told her that when they put up posters, they got vandalized and got repeatedly ripped down.
Thank you so much for that. That was really inspiring. I guess my question would be, if you had one piece of advice or recommendation for people who work in public relations, for research infrastructures or science communicators, to help improve diversity and inclusion in STEM, what would be that recommendation or that advice?
I think just to try and listen as much as possible to the audience or whoever is nominated to represent the audience, and ask them what they need and actively look how to help them. One more.
What gets you excited every day to do science, to do your job?
I think that the idea that hopefully if science communicators do a really good job, then someone who finds science intimidating or scary could change their mind and find it fun. Yes?
I'm just curious from a different angle, what are you currently doing in your research right now?
I've actually left academia and I'm working as a journalist.
How many of the particle soft toys do you have, and do you sleep with them?
Don't have any others, sadly, only Toppy. His job is to stay with my computers and maintain them.
I think there's an opportunity to increase diversity.
Yes.
Yeah. So you talked about your mentors and role models. Could you give an example of how you saw them and why you saw them as a role model? What did that mean to you?
There was someone who just had the courage to be who she was and not try to fit in with what other people thought she would be. And I met her at a time when I wasn't as confident as I am now.
There's a question from online, from Petra, who is asking, why did you turn your back on academia?
Partly, I really enjoy constructing arguments in English rather than in coding. And if I stayed in academia, I wouldn't be able to explore my skills in writing as much as I would have wanted. Or want. Oh, was there just one more question?
Yeah, sure.
You mentioned about when it comes to increasing diversity and inclusion, about listening to people from those groups which you want to include for the diversity inclusion. Do you have any groups or organizations you may suggest which we can get in contact with or listen to, which could be helpful in that regard?
minority in general that tigers and them and not enough for them get together. I was even community but now trying to help all minorities.
There are many groups aimed at minorities in general, such as Tigers and STEM. It started primarily at looking at LGBTQ plus community, but now it's looking at others as well.
We'll have to wrap it up. Thank you so much. Can we thank Claire again, please?